Okay, so in this video, we will sketch the graph of the following function. And of course, we begin by finding the first and second derivative. But before we differentiate, we can rewrite the square root function as a power of 1/2. So that when we differentiate, we clearly will use the power rule. So let's find the first derivative. This will give us, well, 1/2 times 4 is 2. So 2 times x to the 1/2 minus 1 negative 1/2. Then minus 1. So we now have the first derivative. The second derivative, again with the power rule, negative 1/2 times 2 is negative 1, times x to the negative 1/2 negative 1, negative 3/2. And of course minus 0, as the derivative of 1 is 0, since 1 is a constant. So we have the first and the second derivative. So next we will of course try to find the zeros of the function, then the critical points, and then the inflection points. So we want to try and rewrite and factor these three functions. So we have here a common multiple of x, but here the power is 1, here the power is 1/2. So we can factor at most a power of x to the 1/2. And if we do so, then we're left in the first case with 4. And in the second case, well, if you take from 1 1/2, you're left with 1/2. And we can rewrite this now back into the square root form. So root of x times 4 minus root of x. Now here, the negative exponent can be brought down to have a positive exponent. So we have 2 over, and then x to the 1/2 is the same as the square root of x. So 2 over root of x, then minus 1. And since we will try and find the zeros of the first derivative, it would be easier to have a single fraction. So we can put this on their common denominator, being root of x. So this will become root of x over root of x. So on top, we get 2 minus the square root of x, all over the square root of x. And here there's a single term, and we'll go with a positive exponent. So we bring x down, and we are left with, quite simply, negative 1 over x to the 3 over 2. Now, before we find the zeros in each case and the points, if anywhere the expression may be undefined, we have to make a small but key observation. If you look at the original function, this is not a function that is defined on the entire real axis. Now x exists everywhere, but not the square root of x. The root of x is only defined for non-negative values of x. So we have a huge restriction on the domain of this function. The domain, if I write it here, of our function is the non-negative real axis. So the function is not defined for negative values of x. So let's see if we can find zeros of our function. So when is y equal to 0? Well, let's find the zeros, if any, from the factored expression. So this can only be 0 if root of x is 0, in which case x is 0. Or if 4 minus root of x equals 0, but that would imply root of x to equal 4. If you square both sides, then x must be 4 squared, which is 16. So the function has two zeros, one at x equals 0, the other at x equals 16. The y-intercept is always trivial to find. It is the point at which the function crosses the y-axis, so the y value at x equals 0. And we've already found that at x equals 0, the result of y is equal to 0. So nothing new here. Let's now look for the critical points. So we will first look for critical points of the first type when the derivative is equal to 0. And we'll use this form. So if a fraction is equal to 0, then the numerator is equal to 0. That would imply root of x to equal 2. Square both sides, therefore x must equal 4. So we have a single critical point at which the derivative is equal to 0, but since we have a fraction, we have to be careful that this could be undefined. So I will write it like this. So y prime is equal to, and I will use the empty set notation to say that y prime does not have a value. Therefore, y prime does not exist. And when we have a fraction, we have to be wary of a division by 0. And so if x is equal to 0, then we have a 2 over 0 case, which is undefined. So we now have a critical point of the second type, a value of x at which the derivative is not defined. What about possible inflection points? Again, we look at the first type, where the second derivative is equal to 0. Well, the second derivative is negative 1 over a positive power of x. 1 is never 0, so here there is no solution. What about if the second derivative is undefined, so it doesn't have any value? Well, again, we have to be wary of a division by 0, which happens again when x is equal to 0. So there is no possible inflection point of type 1 where the second derivative is 0, but we have a possible inflection point of type 2 at which the second derivative does not exist. As always, now the next step will be to classify the critical points to figure out what does the graph of the function look like around x equals 4 and x equals 0. Now before we do, since we have a critical point at which a derivative is undefined, let's look at this a little bit more closely. So what we will do now is investigate the value of the derivative around the point x equals 0. Now as the function is only defined for non-negative values of x, we will be approaching 0 coming in from the right. So I'll put this here. So let's replace the derivative by this form, so 2 minus root of x over root of x. And let's see what the case of our limit is. After all, we knew that the derivative was not defined at x equals 0. So as x approaches 0, the numerator will be approaching 2 over, and as x approaches 0 from the right, root of x shrinks to 0, but is always positive. So we have a 2 over positive 0 case. So as 2 gets divided by a smaller and smaller but positive number, the fraction becomes larger and larger, so the limit is equal to positive infinity. So this is interesting, right? Recall that when the derivative of the function is equal to 0, then the slope of the function is 0, so the tangent line to the function is horizontal. Now, if the slope of the function is infinity, right, that means that at that point the slope is infinite, so the tangent line will now be vertical. So this is the complete opposite of the other critical point. So now with this piece of information telling us that the function is vertical at x equals 0, we can now classify those two critical points. So since we have two critical points, we will consider an x-axis for each one. And here again, we have to be very careful. Two critical points, but coming from a very different type. So the easier one was when x equals 4. At x equals 4, the derivative was 0. So we have a horizontal tangent line. But at x equals 0, as the derivative is infinite, we now have a vertical tangent line. And again, we want to classify those 2 points, so that is figuring out what does the function look like around those 2 points. Therefore, will the curve be concave up or concave down? So we use the second derivative. So here, let us look at the second derivative at 4. And again, we never care about the exact value, simply the sign. Is it positive or negative? So if we plug in here in our second derivative, 4, we have negative 1 over positive power of 4, which is positive, so the result is negative. Since we have a negative second derivative at 4, the curve is concave down and flat at 4, so we have a local maximum at x equals 4. Now this point is more interesting. Since on the left of 0, the function is not defined, and we do not have to worry about this part of the classification, only on the right. And if you look, the second derivative at 0 also does not exist. So what we will do is simply find our second derivative at a point a little to the right of 0, say 0.1. So y double prime at 0.1. And again, we only need the sign of the expression. So replace x by 0.1 in the second derivative, and you get negative 1 over a positive power of 0.1, which is positive, so the result is negative. So the curve is concave down at x equals 0, and vertical at that point. The only option is for the curve to look like this. Now, if the function was defined for negative values of x, we would have also found the second derivative at, say, negative 0.1 to figure out if it were concave up or concave down to get the other half of the function. But here there is no other half, so we now have a proper classification of the critical point x equals 0. At this point, the function has a vertical tangent line, so the closer we get to x equals 0 from the right, the closer the function becomes to being perfectly vertical. So all we're missing now are the exact y values to the x values of interest. Our zeros, y-intercepts, critical, and possible inflection points. So let us construct our table of values. So what were the x values of interest? Well, those were 0 and 16. And those are two zeros of the function, so y is equal to 0 in each case. Then x equals 4 was a critical point where the tangent line was horizontal. So let's plug back in here or in here, doesn't matter. X equals 4. Root of 4 is 2. So we have 2 times 4 minus 2 is 2. 2 times 2 is 4. So the y value is also 4. And the other critical point was x equals 0. We already have it. And the other possible inflection point was also x equals 0. We already have it. So we only have 3 points of interest. And since the function, again, is only defined for non-negative values of x, we do not need to extend the x-axis along the negative portion of our graph. The x ranges from 0 to 16, so we can go in steps of, say, 4. And the y values range from 0 to 4, so we can go in, say, steps of 1 here. Let's include our 3 points. So we have the point 0, 0, the point 16, 0, and the point 4, 4. Let's include our classification of our two critical points. So at 4, the curve is a local maximum. At x equals 0, our other critical point, the curve becomes more and more vertical. And at x equals 0, the curve is perfectly vertical as the tangent line is the y-axis. And if you look between x equals 4 and x equals 16, there are no critical points or inflection points, so the curve cannot change its behavior as it is decreasing concave down. It will remain decreasing concave down on this entire interval. And past x equals 16, there is no other critical or inflection point. So as the curve is decreasing concave down, it will remain decreasing concave down forever. So the only question now is, where is y going as x tends to positive infinity? So could we perhaps have a horizontal right asymptote? On the left, no need to check as the function is not defined for negative y values. So we will now find the limit as x goes to infinity of y. I will use for y its factored expression. So root of x times 4 minus root of x. And now, as we will see, the case will be trivial. As x tends to infinity, root of x tends to infinity. Then times. Now as x goes to infinity, root of x again goes to infinity. But 4 minus infinity goes to negative infinity. So we have an infinity times negative infinity. Of course, the limit is negative infinity. So as x becomes larger and larger, so as x goes towards the right, y shoots down towards negative infinity. So it will keep decreasing like this forever, so we have no right horizontal asymptote. And we can finally label the key points. Now here we had initially what we thought was a local maximum, but as it turns out, it's clear that this point is a global maximum of the function. As the curve is concave down always, there is no inflection point. And recall that the point x equals 16, y equals 0 is simply a 0. Nothing really interesting going on here, but the point x equals 0 was a key critical point at which the curve is perfectly vertical. And that's it.